Welcome. Today we'll talk about the analysis of sequential circuits. We already know that this is a typical sequential logic circuit. We have a combinatorial logic and we have a memory. From this circuit we can deduce or we can analyze equations, and these equations would give us the behavior of the circuit. However, neither the circuit nor the equations are going to give us a full understanding on how the circuit behaves. So because of this, we are going to introduce to a new concept that is called state table and state diagram. The functional relationship between inputs, outputs, and states are shown in a state diagram. The state diagram is a graphical representation of a sequential circuit. In this case, the states are shown as circles, like this. Here I'm showing you a state that is called standby. The state transitions, which are when you change from one state to the next or to another one, are shown by arrows. And each transition is always labeled with the corresponding inputs, which we will be calling x's, such as this. So in any arrow, you must have an x. And the outputs can go either in the arrows, which is in a Mealy state machine, or it can go in the states, which is a Moore state machine. So you can have either this, which is a Mealy state machine. So in the arrows you have the zetas, or you can have this. Inside the states you can have the zetas. So here's a Mealy state machine. Notice how we have two states, which is y0 and y1. And we have a transition, which is the arrow, which is telling us when we're going to change from y0 to y1. And we are going to change from that state to the other one given the input x. This is the state diagram. And this is called the state table. This state table shows us in this side, it shows us the current state, and on the upper part it shows us the inputs. And basically it tells us when you're in y0 and you have the input x0, then you're going to go to state y1 and giving the output of 0, 0. So what happens if I have a new state? Let's assume we have another state going from y1 and we have another transition to a new state. And this new state, I'm going to call it y2. And in order to go from y1 to y2, I can actually have the same input, but I'm going to put a different input. I'm going to put x1, which is a different input. And I'm going to have, of course, an output. This output, again, it can be the same or it can be different. In this case, I'm going to go with the same output. It's going to turn on zeta 0. So what that means is that I have a new input. So I should put here x1. And I also have a new current state, which is y1. So if I get the input x1 and I am currently on state y1, then that means that I'm going to go to a new state, which is called y2, and I'm going to generate the same output, which is called zeta 0. This is the way you can relate between the state diagram and the state table. This, on the other hand, this is the Moore state machine. So you can see that instead of having the zetas on the arrows, now we have the zetas on the states. And here's how you represent the state table. Let's assume, as we did before, that you have a different choice from y0. So what happens if I have y0 and I have a new state here? In this new state, I'm going to call it y2, and I'm going to get the output zeta 3. So if I have that, I cannot have x0 because this would be the same input as this one. And then the circuit would not be able to realize or to make a decision on where to go. If I have the same input, I should go only to one place. So it cannot be x0. So I'm going to put x1. It's going to be a different input. When I get x1, I'm going to go from y0 to y2. So if I have that, I should have a different column. So I'm going to put here what happens if I have x1. Here I am in the same current state, but I have a different input. So when that happens, I'm going to go to state y2. Of course, if you see zeta 3 is not appearing on this table, and that's because yes, zeta 3. That's because I haven't put here y2. And once I put y2, then I'm going to say this is going to generate zeta 3. So here's a comparison. You can see that both machine states are very similar, with the only difference that the zeta it's either in the arrows or it's on the state. And in order to clarify this more, if zeta depends on the input, then we have a Mealy state machine. And if zeta depends on the states, then it is a Moore state machine. How are you going to realize that? Well, first of all, if you are analyzing a circuit, you should analyze what the zeta function is like. If the zeta has some dependent on x, or I'm going to write it in another way, if zeta is a function of x, then it means that we are handling a Mealy state machine. So here we have an example. This is a state diagram. We have 4 states, which are called A, B, C, and D. And we have a lot of transitions, which are the changes from each state to the next state. And because of this, we also know that this is a Mealy state machine. Why is this a Mealy state machine? Because the zeta, it's on the arrows. Remember, this is always going to be x, the first set of inputs, or the first set of ones or zeros. And when we have the slash, the second part is going to be the output. So analyzing this, we can get this state table. If you check any row, for example, let's analyze row number 4, which is the current state D. That means if we are located in this state, what happens? Well, first of all, if I have an input of 0, you can realize that if I have an input of 0, then this is the arrow that I'm going to follow. So if I follow that arrow, because I have this 0 here, that means that I'm going to go to state A. And I can see that that's correct. I am going to state A. And I'm also generating an output. Remember, this is zetas. And I'm also generating an output of zeta 0. So both of these representations, either the state diagram or the state table, both of them are better representations of what our sequential circuits do. Here we have this circuit. This is a sequential circuit, and this is not only a sequential circuit, but this is also a synchronous sequential circuit. And that is a synchronous sequential circuit because of the clock. The clock is going to tell us when the circuit can change. So this is not a latch, this is not a gated latch, this is a flip-flop. So in order to analyze this, we need to get the equations. The first equation you want to focus on is the inputs of the flip-flops. So in this case, we have a T flip-flop, and T is going to be equal to the OR between X dot Q. Now notice here how I'm putting Q with small caps, and this is important. Remember that when we have Q with small caps, it means the previous state, and when we have Q with capitals, it means that we have the next state, or X inverted dot Q inverted. This would be the equation of the input of the flip-flop. The other equation that you want to consider is zeta. So in this case, zeta, it's equal to X dot Q. So those are two equations. This is the way we begin the analysis of the circuit. So we already know these two equations, and now we want to see how to get the state table and the state diagram. So we're going to start as if we were writing a truth table. And for the truth table, we're going to consider the inputs. In this case, we only have one input, which is X. And we're going to consider the states. The states are going to become part of the input. Remember that states are the combinations of the memories. So in this case, we only have one memory. Because of that, I'm going to put just Q. And those are my two possible inputs. And I'm going to go with the analysis. Now, what I want to know is what happens with Q in the next state. I want to see how it behaves from one state to the next. Now, in order to get that, I actually need the behavior of T. Because remember, this is a T flip-flop. And a T flip-flop has the next behavior. So in order to understand how the Q is going to behave, we need the behavior of T. So we analyze the equation t, and we're going to see that this is going to be 1 when both inputs are 1, or when both inputs are 0. And here is going to have a 0. That's the behavior of t. So with that information, we say when we have 0, we're going to have the same output or the same Q that the one we had before. So see, if we had a 1 before, we're going to still have a 1, and if we had a 0, we're going to still have a 0. Now what happens when I have a 1? If you see in the behavior of the T flip-flop, when you have a 1, you're going to invert it. So from going to Q 0, we're going to go to 1, and from 1, we're going to go to 0. So this is the behavior of the flip-flop. Now another thing that you want to do in this table is get zeta. So to get zeta, you are going to analyze its function, of course, and you see that the function is qx. Now here's the importance of putting the correct way, which is q with small caps. So zeta is going to be 1 when q is 1, and with x when x is 1. So this is the only way when zeta is going to be 1. In all the other cases, zeta is going to be 0. So that's it. That's all the behavior of our circuit. So now let's build first the state table. So for the state table, remember, we need the current state and we need the inputs. So how many inputs do we have? We have two possible inputs. We have x being 0 or we have x being 1. And how many states do we have? Well, we have two states possible. The memory can be either 0 or it can be 1. Now here, how do you read it? Well, if this one here, see it as Q with small caps, and what you're going to write inside the cells is going to be Q with Q with capitals. So if you are in Q 0 and you have an input of 0, that means that you're analyzing this row. And in this row, you have that Q is going to be 1 and zeta is going to be 0. Then on the next column, when you have x equal to 1 and q with small caps equal to 0, that means you are analyzing this row. And in this row, you have that q is going to be 0 and the output is going to be 0. If you analyze the next row, that means that q is going to be 1 and with an input of 0, and this is this row. And with that, you're going to go to 1 with an output of 0. And finally, you're going to go with the final row, and you're going to go to Q0 and an output of 1. So this is the state table. Now with this state table, we can build its state diagram, and we only have to do is we want to write the states. And in this case, we only have two possible states, the state of 0 and the state of when the memory is 1. And we need to find the transitions. So again, it is a matter of analyzing what happens. So when you are at 0 and you want to have an input of 0, so input of 0, you're going to go to state 1. This is this particular cell. And you're going to generate an output of 0. Now when you're at 0 and you have an input of 1, then you're going to remain at 0. And you're going, I remember this was with an input of 1, and you're going to generate an output of 0. Now when you're on state 1, then if you have an input of 0, you're going to remain on state 1 when you have an input of 0. And you're going to generate an output of 0. And finally, when you're in state 1 and you have an input of 1, you're going to go to state 0 and you're going to generate an output of 1. So this would be the state diagram of this circuit. Let's develop the state table and the diagram, the state diagram for this circuit. Now for this circuit, it's a little different. You need equations for the inputs of the flip-flops, remember, and the output of the system, or the outputs of the system. So you have the inputs of the flip-flops. Now here's the interesting part. You have two flip-flops. Now when you have two flip-flops, That means that you can have 4 different states, because remember, states are the combination of the outputs of the flip-flops or of the memories. So we are going to name this flip-flop as flip-flop 0 and this flip-flop as flip-flop 1. So because of that, since we have 2 inputs that are called J, then we need to say what is the input of J0, but also what is the input of J1. We need K0 and we also need K1. And at the end we need zeta. These are the 5 equations that are going to determine the behavior of our system. So these are the equations. If you analyze the previous circuit, you're going to get these equations. And let's analyze how to build the state table and the state diagram. We need sort of a truth table in which we have the inputs and the states or the memories. So these would be the inputs. And in order to get the behavior of the system, we need to analyze what happens with the memories. So the memories would be Q with caps 0 and Q with caps 1. Now, in order to get Q0, we need to analyze what happens with J0 and K0. Again, important, this is going to give me the behavior of this. We also need to analyze what's going to happen with J1, K1, and this is going to give me the behavior of Q1. And at the end, we also need zeta. So now we are going to put all these equations in the table. So there I have the behavior of J0, K0, J1, and K1. With that information, we can know how Q0 and Q1 is going to behave. In order to know how they're going to behave, we need to remember the behavior of the JK flip-flop. So this is the behavior of the JK flip-flop. So we're going to see where we have those combinations. For example, here we have combination 0, 0. So when we have 0, 0, it means that Q is going to remain. So Q0 is going to be the same as Q0 with small caps. So it's going to be 0. When we have 0, 1, which is in all this section, then we're going to have a 0. So very easy to analyze. And when we have, okay, we also have another 0, 0 that I forgot here. And when this case Q0 is 1, so it's going to remain to 1. And we also have 1, 0. And 1, 0 means on. So this is going to be the behavior of Q0. Now we analyze Q1. So for Q1 it's the same. We see that in this whole section it's a reset, so it's going to be 0. And below we have a 1, 0, which is going to be 1 over here, and a 1, 1. And remember, when we have a 1, 1, we're going to invert its previous state. So here Q1 is 0, so it's going to invert to 1. Here Q1 is 1, so it's going to invert to 0. And that's how we get the behavior of our system. Finally, we get to zeta, and zeta is Q0, Q1, X. So here's the only way where zeta is going to be on. When you have this type of problems, sometimes it's better to rename the states. So for example, you have when Q0 and Q1 is 0, 0, 0, 0, then you might want to name this as, or you want to give this state a name. So I can say this is state A. So by doing that, you can see, for example, that here you have 0, 0 as a combination of the outputs. So you have state A here. And you're going to state 0, 0. So you also have state A. With this, you can build the state table and the state diagram. So I'm not going to give you the solution in this video. I want you to try to get the state table and the state diagram. Some hints. We have 4 different states, so you should have something like this. You have one state here, one state here, one state here, one state here, and you have A, B, C, and D. And you have 2 arrows coming from each state. What you have to determine it's where those arrows go. And that's done by building its state table and the state diagram. Thank you for watching.